Hey Audrey. Okay. Yeah, I looked at this problem and I went through it and I totally see we were on the right track and then I see where the mistake I made was. And so let's go over this problem. It's a little bit easier than I was approaching. I was trying to approach it this algebraic way and do smart number stuff, and you don't have to do that actually. So let's look at this problem again. Let me zoom out a little bit. So we had all the right equations. So Mr. Green, he's doing the sale for Bastille Day, and we had these equations here. I'm going to say before, when I was working the problem with you, I had G or P for potted plant and B for basket, and that makes sense because um, those are the plants. But I'm going to say X is the giant potted plant, giant potted, and Y is the hanging basket. And I think um, that's just so we can use it in Desmos, because we're going to solve this with Desmos, and it'll be much easier if we use X and Y. And that was the first mistake that I was having before. I just kind of, yeah, I messed up on there. So we know that we had these equations here that if we think of square footage, giant potted plants take 7 and hanging baskets are 4 square feet. And in total, he has 168 feet of room, right? So 168 feet of room. So we can say for every giant potted plant, this will be 7 times x plus 4 times y. That's the amount of space these plants will take. It has to be less than, or it could be equal to 168 feet, that's square feet. If we look at gallons of soil, same thing, 14 for the giant potted plant and 2 gallons of soil for the hanging basket, and that has to be less than 210, the amount of soil that Mr. Green has. And then the last thing is the price. So it's going to be $14 for every giant potted plant plus $5 for every hanging basket, and it has to be less than or equal to 252 because that's his budget. Right, so those are our variables, and these are the equations. And if I wanted to write the objective function for profit, I think we wrote that the right way. I know that profit is going to be equal to he's and this is what it should be. It should be he's selling $28 for every potted plant plus $14. Was it how much was it again? $8. Sorry, $8 for every hanging basket, and really it should be minus the cost. I think that would be important to think about because what profit is. You have to take into account how much you pay for the plants to begin with. Okay, so from here, now that we got that squared away, we can use Desmos. So I'm going to go to Desmos, and I've already kind of been working on it. So if I look at the first equation, 7x plus 4y is less than or equal to 168. And I could say, maybe I can even, in Desmos, if you put these curly brackets, you can add restrictions for x. So x is going to be less than, or I'll say x is greater than or equal to 0. Right. So for this equation here, because you can't, you can do x or y, right? Because x or y, that's representing the amount of plants. This is for space, I believe. Space. If you have 0, if you bought 0, if x was 0, if you bought 0 giant potted plants, you could have 42 hanging baskets because of the amount of space they take up. Or you could buy 24 giant potted plants and have 0 the hanging basket because of space. So the amount of a giant potted plants you could have is anywhere between 0 and 24. Those are you could have any combination of those. You could have, let's see what else is here. 10, what are some other combinations, some whole numbers here. Any of these combinations you could have. But you could have at most 0 giant potted plants, and you could have 42 hanging baskets, or you could have 24 giant potted plants and 0 hanging baskets. If you're just thinking about meeting this condition, the space condition, the amount of space you have. Now, the second equation we had was soil. The soil you have. And so, if I get rid of the purple for a sec, the red one. So you could have 15, for the amount of soil you have, you could have 15 giant potted plants and 0 hanging plants, or you could have 105 hanging plants and no giant potted plants. It's a very, very steep line because the slope or the difference in soil is so big. A giant potted plant takes 14 gallons of soil versus a hanging plant only takes 2. So it's pretty drastic here with the difference there. Now, if you use both equations, that anything in the double shaded area right here, so anything in this double shaded area could be both. Any of these double shaded areas are going to represent where you overlap. You could have both. You could get like 0, 0. You could have 0 of either plant, and that would be okay because you wouldn't be using any space or any soil. But you could use, like, for example, 10. You could easily get 10 of each. You get 10 giant potted plants and 10, because that's definitely, right, if I make that point, 10, 10, 10, 10, right here. That's definitely in both shaded areas. So you could have 10 of each plant, and you have enough space, and you have enough soil. So that's just an example there. Right, so there's your second equation. Our last equation here, the orange one, is now the money. How much money or your budget? How much can you spend? There's that equation, right? And so now looking at what points and what are like the special points, the significant points where you're under overlapping the orange, the red, and the purple. So this point right here, 0.42, that's definitely in the purple area and in the orange area and in the red area. So 0.42, that's an important part. 0.42, have that. I'll put that in, let's put it in blue. Right, because that one, you could have 0 potted plants and have 4 hanging basket plants. That one's okay. This other one right here is underneath orange, purple, red, 8.28. You also have, so this point here, 12.21, that's red and purple, but it's not orange, so that doesn't work. But this point here works, 13.14. That one works. And then the last one here, 18, no, not that one, sorry, 15.0, right? 15.0 is underneath the red, it's red shade area, purple shade area, and orange. So 15.0 is another point that is underneath. So these 4 points, I'll say are significant points because there were a couple lines intersect. So they would be like the maximum there. There are more points that are anything here, again, like 10.10, that is underneath all the shaded areas. 10.10 is, so is 5.5. All of these points are underneath the red, orange, purple, but these here, these 4 points are sort of at maximum. So this point here, 15.0 is the maximum you could get if you're only buying giant potted plants. This point here at 0.42 is the maximum you could get to meet all the conditions if you're only buying hanging basket plants. This point here at 8.28, 8 giant potted plants, 28 hanging plants, and there's this point here, 13.14. Those are all points that are good. So let's write this down, and let's just then compare. We'll compare profits, right? So 0, 42, that's a possibility. We got 8, 28, that's a possibility. We have 13, 14, that's a possibility. And then the last one we have is 15, 0. That's a possibility. Given these three equations, you just, again, in Desmos, you just graphed them, three equations. You don't have to, like, in the top one, I put like some sort of restriction here. You could put a restriction on domain if you wanted to. For like the red one, it's going to be 0 to 15. You could order 0 of the plants, or you could order 15 of the plants, right? That's one way. If you just want to, you don't have to put those restrictions there. That's just, it might make it easier to see it because you don't have to worry about like the negative space or whatever. It doesn't really matter here. But these are 4 points that we're thinking about. 4 points that meet these conditions. If I plug each of these points into these three equations, you'd always be true. There'd be nothing that would be wrong. Like any other point out here, like 20, 30, like that wouldn't work. You wouldn't have enough space or enough soil or enough money to buy those. These 4 points all work. Now we're going to check and see which of these works more. So write the system of linear inequalities. We did that. There should only be 3. Again, I don't know what that means. If you graphed it, again, that's what we did here. We graphed it like right here. Now, if you were going to graph it just for the sake of graphing it, let's we can graph this. If I was going to graph it, I would. So we'll do it really quick. I'll do it on a different piece of paper. So I don't have to go back to that. If I was going to graph this example here, 7x plus 4y, I would make it 4y is less than or equal to negative 7x plus 168, right? Just kind of move the 7x over and then divide by 4, get y is less than or equal to negative 7x over 4, or negative 7/4 x plus 27. So it's going to graph that line, which I can do pretty easily. Let me graph that. Graph the line. I'd start at 27. Let's say 27 is about here. And I think I went to down 7 over 4. It's going to be, what would this be? Sorry, let me think for a second. If y is 0, x is 28. So it'd be something like this. And imagine that everything below that is shaded. That'd be the one graph here. Everything below this is shaded. Let's do another graph. Let's do blue. So the next one here, this 14x plus 2y is less than or equal to 210. So same basic idea. Subtract negative 14x, and then divide by 2. You get negative 7x plus 105. So let's graph that line. Again, I'm putting it in slope-intercept form because it's easier to graph. So 105 is way up here, right there. And then, where's y0? It'd also be 0, 7, 28. So it should also be that. Should be that line. This one here. Wait, nope, sorry. 105, 0, 14. What's 210 divided by 14? 15. Okay, sorry. So 105 to 15. So just so you know, the way I know the y-intercept because obviously I put it in slope-intercept form to get the y-intercept. That's pretty obvious. The other way I'm doing it is in this form here. We wrote these inequalities in standard form, that standard linear form. To find the y-intercept, at the y-intercept, these points right here, these points down here on the x-axis, that's the x-intercept, that's where y is 0. So if you covered up the y there and said 14x equals 210, and then you just do 210 divided by 14, you get 15. So that's why I know that would be the x-intercept at 15. So that's how the quick way to find the intercepts there. Then our last line, if we're going to graph it for this worksheet, it's right here. You could, again, to graph it, I'd maybe subtract the 14x, so negative 14x plus 252, divide by 5, divide by 5, divide by 5. Get y is less than or equal to negative 14 over 5x plus 50 point, I think 50.4. 252 divided by 5 is that. So the y-intercept is 50.4. The x-intercept would be 252 divided by 14. So let's see, 252 divided by 14, 18, which is 18. So 50.4, get a different color here. Do that. 50.4 is about there, and I'm going to 18, which is about there. Okay, so those are your three lines. It'd be shaded below, underneath them for all three. If you're going to graph them. And this point right here, if I was going to make a point, if you had to guess that point, it's definitely, mine's not to scale, but I'm pretty sure that that point would be 13, 14. This point right there. Those are all three of those intersect at 13, 14. Right, and that's what we got when we were doing it in Desmos. So in Desmos, they also intersected. So it sort of looked like that, right? This is now fits there. So hopefully that helps you graph it. Okay, and then find the vertices of the region that contains solutions to the systems. So when they say find the vertices of the region that contains the solutions, what does that mean? So let me make this bigger for a second. I'd say the region that contains the solutions, I could maybe make this even, try to make it as clear as possible. So 0 is less than or equal to x, less than or equal to 18. So this point here, here is a point, there's a point. So the space that's triple shaded, that's the area of the solution. That's the space that has all the possible solutions. So again, like 10, 10, what's that going to be? 4, 10, right? Because it's all going by twos. Any of these spots that's in this area right here, those are all possible solutions. Now, a possible solution also is 0, 0, right? That's also a possible solution. And if I want to be like super precise on these to make this look well, I think I can add another bracket here. I'll say y is greater than or equal to 0 on all of these. So let me just copy that. Ooh, negative 0. No, y is greater than 0. Okay, so now we can really see this area. Notice there's nothing in the negative area because you can't have negative plants. You can't have negative plants. That doesn't make sense. So all the points really here in this double shaded area, right? This is like this weird little shape here. There's it's technically a pentagon, a weird looking pentagon. So you have the y-axis, the x-axis, and this line here, and then this line there, and then that line there. That's the all shaded region. So you have 5 points that are possible. 0, 0 is a point that's possible. 8, 828, that's where they all that's possible. 13, 14, 0, 42, and 15, comma 0. These are the 5 points that are all the vertices of this area of solution. Again, this five-sided shape here. It looks mostly red, like this red, orange, purple sort of thing. Right? Like this area here is orange, that's not good, and this purple area is not good, and this area right here is purple and red, but it's not orange. That area is just red. This area is orange and red. So this area here, that's the triple shaded area. Okay, oh, I hope that makes sense. So those are, right, those are the five points. Now it says test the coordinates of each vertex in the object function to find the one that gives the maximum profit. Maximum profit. That's what we're talking about. So we have our points here. These are our points, and I'll add 0, 0. Now you don't have to test 0, 0. There's no profit. How are you gonna have profit if you don't buy any plants? So that's a possible solution, yes, but is it practical? No. You're not gonna buy 0 plants. Okay, so let's talk about here. If you only buy 42 of, remember this is like an XY ordered pair. So this is 42 hanging basket plants. You can buy only 42 hanging basket plants. That'd be fine. Not a problem. You could do that, and let's see how much money you would make if you only bought 42 of these plants. So first off, let's think about how much that would cost. So 42 times each hanging basket plant is $5. So 42 times 5 is 210. That doesn't seem right. Oh, okay, fine. It is right. So 42 times 5 is 210. So if you bought only hanging basket plants, it cost you $210. Now let's think the profit. The profit there would be equal to 28 times x. Well, here you bought 0 of the big plants, plus 8 times y, 42, minus 210, which is what you pay for it. So really, now that I'm thinking about it here, let's change our profit. Here we had profit is 20x plus 8y minus cost. Let's think about that again really quick, now that I'm actually thinking about profit. I'll write that again, 20x minus, 20x plus 8y minus the cost. Well, the cost is just this equation here. That's the cost. So 14x plus 5y, right? That is what the cost is really. So really profit, you could say 28 minus 14 is 14. 8 minus 5 is 3y. So this is the actual true profit equation that takes into account the cost. So that's a better one. So again, in this case, if we sell 0 potted plants, but we buy 42 those big plants, or the hanging plants, sorry, it'd be 42 times 3, so the profit 3 times 4 is 12, 6, 126, $126. So if you bought only the hanging basket plants, right? Let me just double check my work. 3 times 42 is 126. Yeah. So if you bought only the hanging basket plants, you make $126 profit, which is not bad, but is it the most? So this one here, $126. Okay, let's try this other one, 828. So 8 giant potted plants, 28 basket plants. So it's going to be 14 times 8 plus 3 times 28. Let's see what that profit would be. I'm just from here on out going to use my calculator. 14 times 8 plus 3 times 28. Right? Because you've got, there you go. So 196. So if you were to buy 8 giant potted plants, 28 hanging plants, you'd make $196 if you sold it all. If you take into account the cost and the spacing and all that, which is more than 126. So right now, that's the winner so far. All right, let's now do 13, 14. So now we'll do this again. 14 times 13. That's if you bought 13 of the potted plants, the big old potted plants, and you bought 14 of the hanging basket plants, what's that profit going to be? So 14 times 13 plus 3 times 14. 224. So now that's definitely the most money so far. And then the last one, the last possible case, what if you only bought 15 giant plants, didn't buy any hanging plants? That's just going to be 15 times 14. 15 times 14. 210. And so this one, this is the amount of plants you should buy to maximize your profit. If you bought 13 the big plants and 14 of the hanging plants, you would make potentially $224 if you totally sold everything, which is the most amount of money. So state the solution in terms of the variables. State, let's see. So yeah, testing, and that's all the work we showed here for number 6. Number 7, if you're going to state in terms of variables, I say something like this. You would make the most money if you bought 13 giant potted plants and 14 hanging basket plants. The profit would be $224. Something like that. That's stating your solution in terms of variables, right? So there's different ways you could do it. I mean, you don't have to buy that many plants, but that'd be the most way to make the most profit if you were to do those plants. So again, the way you solve it, we were on the right track when we did it before. You have your inequalities, then you graph your inequalities. You can graph them. Graph the inequalities. It's easiest on Desmos, right? Because then you totally on Desmos it makes it really clear that you can see where they overlap, where they intersect. There's that point there. And then you test out those points. I wonder if I could also show the profit. I don't know about that. I probably should just call it there, but no, never mind. Forget that. So you graph it, you find the vertices of the shape. So again, the vertices, those are just like the corners of this triple shaded shape. You find the vertices, and yeah, 0, 0, you don't really even have to count. But you find those 4 vertices in this case, and you plug them into your profit equation, and then you see which one's bigger. So that's that whole problem. Ooh, took like half an hour. Now, I will say this. A trick. This is a trick that, I, as a teacher, probably would not want to tell you. But I'm not a teacher anymore. So if I had that problem, right? I'm looking at this problem and I'm scrolling through it. And what if, in theory, I had no idea how to do this? I was like, I have no idea how to do this. And I said, okay, linear programming. Oh, that's interesting. That's a pretty Googleable phrase. What are we talking about here? We're talking about plants. Something about linear programming and plants. So if you just Google, I just Googled, if I go back, let me see what I Googled here. Linear programming potted plant answer. That's what I did. First thing that came up. This is from Texas. Yeah, it's there. It's a lot of reading. This is a slightly different problem, but I realize it's the exact same. It doesn't help us much on a test, but it's just something to check your work. They say the profit is 476, but that's not true. That is not the profit. That's not how profit works. You have to take into account how much you pay for something, but it's still 1314. In this case, this is not cheating. This is checking your work. And even though I disagree with the work here, it did help me kind of work my way backwards. So, for what that's worth. All right, so there's that problem. There's that sheet. That's linear programming. Good stuff. All right, we'll see you later.